you good?
Yeah.
That's good. Yeah, I heard about vendors becoming free, so.
Okay, we'll start out in about 15, 20 seconds.
But the wrong science that I read last week was multiplication expenses. Like, this makes perfect sense. And it was so clear and well written. Yeah. And follow everything. And I was like, look at me writing good papers.
There's no better way to get the whole class to start talking than to say, we'll start in 15 seconds. Better get that last minute of conversation in. So, okay, I think we'll get going. So, welcome back. Stat Inference. We're going to finish up on the Bootstrap, and then we're going to move to the central limit theorem. And I'm going to give you a pretty cheap version of the proof of the central limit theorem. I want to say a few things about it. I like this proof, but it is the easiest one. It's the one that's covered in your book, so you can read through that. Hopefully you've looked through it. We're going to walk through the details of that proof, and I'll say a whole bunch of stuff about how important this is. I will discuss the stronger proof, but we're not going to do it here. We did a class in measure before we were able to tackle that proof. So maybe at some point during your life, try to read through every version of this proof. You'll decide whether or not you're a mathematician, a computationalist, a methodologist. So hopefully it's a little bit of a agglomeration of all those things. So I was a math major, and then I studied computer science for a while, and I tried to put all these things together. So I like a good convergence proof, but saying that, I've got problems to solve. So I have data to analyze as well. And so I kind of gave up a long time ago about being super rigorous about everything. And so I kind of have an engineer's mentality, but there is a mathematician somewhere inside of me. So sometimes I go and I look up, what do you need to prove this in the strongest form? And so people have been playing around with this proof for a long time, and it kind of evolved. You can say a lot of things about what actually happens to averages. Okay, before we jump back into our example that we'll finish up in 5-10 minutes, what is this thing where we just continue to repeatedly sample with replacement from our original data set, constructing bootstrap replicates, and evaluating our statistics so that we come up with a bootstrap distribution? Why is this called bootstrapping? Does anybody know? Yeah.
Is it from like the terms lifting yourself up by your bootstraps?
Yeah, that's it. So it's like the worst named algorithm in the world. But you can kind of imagine you have some test statistic that you want to compute, and you want to understand its distribution, and you don't know any theory. So it might be so complicated you can't work it out even if you did know a ton of theory. And so the question is what do you do if you don't understand all the asymptotic properties of everything and you can't work everything out? I guess you just give up and go home, right? So that's not what we do. So we try to do something. So there's this term, sometimes you just have to lift yourself up by your bootstraps. Now I don't have straps on my boots, but it's kind of a very strangely named algorithm. So it's named after a colloquialism. You can tell a statistician came up with this name. So anyway, we got to work on our naming convention. Saying that, it's so ingrained in us, we're just going to continue to call this the bootstrap. But it's like that conversation that we were having last time, where I walked through the statistics department at my old college, and I'd hear people say, well, I'm going to bootstrap it. It's because they couldn't do the math up front or something like that. And so it's an easy technique, especially if you have IID replicates, to basically answer any question you want. You might not be answering it in an optimal way, but at least you can come up with an answer. Please.
Yeah, I just want to clarify something. So I said, I want you to confirm. So basically you have, let's say, n samples, and you still have to replace them b times, say b times a.
Let me correct that.
Yeah.
You sample with replacement n times, and then you follow that procedure cap b times. So each bootstrap replicate is going to be a vector of size n, the same size as your original data set. So there's two types of asymptotics going on here. There's cap b, the bootstrap replicate, and there's cap n, the number of replicates that you saw that's in your data set. So for every iteration of those cap B iterations, you're going to sample with replacement n times. And so that you have cap B data sets, all of size n. And they're all a little bit different.
And the R, how many times do you get those?
Yeah, so in my code, I call that cap R. So my bootstrap replicates, maybe I should have called that, oh, sorry.
R is the B. Yeah.
Gotcha. You don't like my comment in here. Let me fix this because it's not labeled correctly. So replicates from the population, this is going to be bootstrap replicates. Yeah, nothing like a bad commented piece of code, especially when the comment's wrong. So code still functions correctly, but that's going to be my number of, oh.
Isn't that your true population?
You're right. 9 o'clock in the morning. What cap R is in this is when we did our experiment, we went back to the population cap R times.
Yeah.
And then I got my bootstrap replicates.
And you continue with the last one, right?
That's right.
Okay.
So yeah, this was the cap R. The number of times I went back out into the population was kind of the fictitious part of the analysis. I'm saying I could do that and have this tireless scientist go back out into the population and collect me cap R replicates from that population, all of size n. And then we compare that to all of our bootstrap replicates. Okay, good question. So this part of the code, right here, where I'm just getting cap R replicates, this is the thing you cannot do in reality. But you're inclined to think about doing this and try to understand what distribution you end up forming. Down here where we do bootstrapping, cap B, this is the thing that you can do. Pick yourself up by your bootstraps so that you can approximate what's happening up here. That's the idea. And then we just plot everything against each other. We've been studying the sample average, and if I saw somebody bootstrapping the sample average, I'd either think their n is so small that they can't use the central limit theorem, but then if your n is so small, I'm not sure bootstrapping will work entirely well. And so if you did want to understand the distribution of the sample average, we can invoke some theory. And so we're comparing these results to results that we kind of understand and understand how this is supposed to work in practice. So if I crank up n, I'm just going to say 100, something like that, and I rerun all this, what we'll notice is that the distribution that we would like to construct, we almost construct using the bootstrap. And so when we can compare those, looking at a QQ plot. So I can't actually do that, go back out, but I would love to be able to do this in reality. I compare those two different distributions. So the distribution I would like to construct and the bootstrap distribution. And they're pretty close to each other. So when I see QQ plots, that's all right. So basically says those distributions are pretty close to each other. I wouldn't say that that's entirely linear. And I would think when I looked at this, I would say, well, the results are off a little bit in the tails. And that's what you can see from this QQ plot, because it's not perfectly linear over in the ends. But I would say it's pretty close. So those distributions are reasonably close. I think what we also did is we looked at a QQ plot. Let's pull up a new figure. A QQ plot comparing the bootstrap replicate to the standard normal. So QQ plot, and I'll say bootstrap. So I'm just going to compare my bootstrap replicates to the standard normal. And they're pretty close. So that's about normal, maybe. If we cranked up n, this should start getting more and more normal. So let's just do that just to see this result. So again, I'm comparing now not two empirical quantiles to each other, but I'm comparing theoretical quantiles from standard normal to my empirical quantiles that I got from bootstrapping. So let's just crank up n a little bit more, run this one more time and see how well this works. So n is equal to 1,000. Starting to get all kinds of information about the tails of that distribution because we're going out and sampling over and over and over again. So I think it's tempting to think, look, I just want the data that is the central tendency, the stuff in the middle. But I always think, I want the stuff in the tails so that I understand the variation in everything. So I always think that the tails are the most important thing. So those distributions are getting closer. There's my QQ plot. Comparing the bootstrap replicates to the population replicates. And now I'm just going to look one more time at this QQ plot where I compare everything to a standard normal. Pull that off to the side. And there we go. So same experiment, we cranked up n and we noticed that our bootstrap replicated means do look about normally distributed, and this is about as good as you get. So if you end up cranking up n really, really high, and you do something like a chi-square test for goodness of fit, eventually you're just going to get extraordinarily low p-values. And so I don't like that chi-square test of goodness of fit because if I have a lot of data, I'm just going to reject. We'll be talking about that later when we get into Neyman-Pearsonian testing. But this plot, for me, I can visually just kind of inspect it. I know it's not going to be perfectly normal because nothing is, but it might be close. And so I like the visualization that says, yeah, it's about normal all the way through. Even the little outliers over here, they kind of don't deviate too far from the line. So that's as good as I ever see in my life. We wouldn't want to use the bootstrap on this for the mean because we do have a theory that we'll get to in a minute. But let's say I had a different statistic and I didn't understand it. So instead of looking at the mean, I'm just going to look at maybe a different statistic. I'm just going to compute the variance. And I could make this really crazy. I could take like the sign of the variance or something like that. Some statistic that I don't even know what the distribution of that is. Word already told us that variances look like some sort of scaled chi-square distribution. But let's say we didn't know that. We could still bootstrap. And that's the cool part of bootstrapping is you can kind of just always do it if you've got IID data. I'm going to run this one more time. Same drawing from the population, but the statistic that we're computing from all of these data sets is now different. I don't think that the statistic that I'm computing is normally distributed. And let's say I didn't have Warren around to tell me, actually, we can figure out what that distribution is. And that was kind of the name of the game all through the 1900s, is write down important statistics and try to figure out what their asymptotic distributions are. That's mathematical stats. So, and that's what everybody did for a long time. I have a different distribution altogether. So these are my distributions that I've constructed. They're not normally distributed. But my replicated stat and the bootstrap replicates are about the same thing. And so bootstrapping still works for us. And I didn't need to do any math. So that's kind of nice. So I would say use the bootstrap when you think it's appropriate. But if you want to write a paper that people are impressed by, you're going to have to do some math. So you can't just bootstrap all the time. I used to be pretty lukewarm on it because I thought it was so boring. But now I find myself telling people all the time, just bootstrap. If you need a real analysis and you want me to come up with my full-blown predictive analysis, we have to work harder. But if you just want a quick answer and you're an engineer and you don't really care about creating new methodology, bootstrap can work for you. And that's what this picture shows. So go ahead and play around with that code. I'm going to have you code this stuff up in the context of an example soon, and we'll be comparing to things that maybe invoke the central limit theorem. So we'll get a lot of practice with this. Are there any questions before I move on? Peter?
Maybe this is more just like a broader perspective question, but like, does bootstrapping bring like anything new to the table other than what our samplers already brought us? Like,
Yeah.
essentially what we're doing is just resampling our sample. You know what I mean? So it's like,
Yeah, so if I just wanted to know, if I wanted to compute like X bar variance, it doesn't help us computing that statistic. So if I think about the example with the mean, then the mean of the mean is still the mean. And so you're not getting a better estimate of the mean. You're not getting a better estimate of the variance in doing this. But what you are getting is the thing that statisticians want, uncertainty. So we get the full-blown distribution. So you're not getting a better estimate, but you're quantifying your uncertainty in that estimate. And that's what makes you a statistician, because you care about that. If you were an optimizer, and you only were going to look at a point estimate, you didn't care about quantifying uncertainty, Bootstrap doesn't bring anything new to the table. Saying that, you should always care about your uncertainties. So I think it does bring something.
Why Bootstrap works? Like, could you explain a little bit intuitively why Bootstrap works?
So the intuition is really the simulation study. That I'm going out into the population and I'm re-replicating everything. So if my data set is representative, if it has the same variation as what we would see in the population, then resampling from that distribution is going to show you all that inherent variability in the population. So I'd say it's really the best explanation I can come up with is this simulation experiment, where I go back out into the population and I resample over and over and over again. And bootstrapping is kind of like that. It's just slightly different because I'm not running back out into the population. I'm resampling from my original data set.
That is, but anyway, it's already there is already difference. Why that difference disappear?
Why are they different?
Why that difference disappears?
Why the difference appears?
Yeah.
Because they're different. It's the best I can say.
I think it's because it's replacement. Maybe if it was without replacement.
Yeah, if it was without replacement, we'd just get back to the same statistic every single time. So basically, we're trying to replicate what sampling looks like. So sampling from a sample is a sample. And so the only thing you're not able to get is extra information about the tails that you've never seen. So you can only learn about variation in places where you do have data. Anyway, if you want to talk more about it, I maybe can give you a better intuitive explanation, but we'll probably need to sit at the board. So maybe some office hours will help in the conversation. Hunter.
Related to Peter's question and what you were saying about statisticians caring about uncertainty.
Yes.
So in the example that you gave about the sample mean, we know that like even if we sample with replacement, the average of all those is probably going to not really improve our estimate.
That's right.
Of the mean. But what it will do is give us some estimator of the variance of X bar, right?
You got it.
Okay.
That's right. That's exactly it. So another rephrasing. We're getting to learn about the variance of X bar or the variance of the variance. So in this example, we're learning about the variability of that variance statistic. So that's something that you want. So yeah, we're learning about the variability. Not just the variability, but the whole distribution, what it looks like. So we get a little bit more than just the technical variance, but we understand how it all varies all together. So what the distribution looks like. Okay. I'm going to move on from that, but that is the important thing in this class, is quantifying the variability of a distribution, understanding how things are distributed, where we expect things to be. There's some true answer, supposedly. We'll never get to know it. We can only estimate things, and so estimating how far off we are is the important question. That's what created the whole field of statistics. Jess?
So it's a parametric way to
I would say this is totally non-parametric. So there is something called a parametric bootstrap, but I didn't invoke any distribution. So if I had a parametric estimator, let's say I was computing, let's say I was working with like a regression. So let's say I had an example like this. Y is equal to x beta, where this is a matrix, this is a vector, this is a vector, plus some error. That's a vector right here. And these would be normal 0, 1s, or 0 sigma squareds. So say I was playing around with a parametric model. Meaning that I knew how these errors were distributed. It's just a vector of these. Meaning that the yi's given xi transpose beta and sigma squared. This might be something like a normal distribution. E to the minus 1/2 yi minus xi transpose beta squared over sigma squared. So this is a parametric assumption on the distribution of these y's given this function. Oftentimes we want to estimate that. So I might come up with a maximum likelihood estimator, something like that. So beta hat MLE, if I maximize over this thing, I would wind up with this estimator. So this follows from a parametric assumption. So what I could do is I could bootstrap over yi, xi pairs, and I have to keep them together. And then I could compute this statistic over and over again. And then come up with a distribution of that statistic. That would be the parametric bootstrap. So what we played around with, just these statistics that we're computing, like the variance or the mean, that was non-parametric. I just wanted to compute those statistics and understand how they vary. So very similar concept. Parametric bootstrap just means you're doing something with a parametric model. So, good question. Any other questions before we move on? Let's get into the central limit theorem. I would say this is probably the best result in all of stats. So it's really cool. Most of you know what it is. It says something like this. So let's say I have some data points. I'll call them xi's. And they come from some model. I'll be specific and I'll denote my distribution with its random variable. This is an instance of that random variable. We'll say this is all IID. And I might not know what this thing looks like. It might be something that's crazy. And I might not know about this distribution. I might not be willing to model that distribution. So I might not be able to understand what the individuals in this distribution look like. But I can say something about the average of these individuals. So while this might be a mystery to us, I can figure out how this statistic is distributed. Just call this x bar n. So the mean. So a lot of times people want to know about the mean. What's happening on average? Now I would say that's not always the most important question if we think about things like medicine. I might not care about what happens on average. I want to know what happens to individuals like me. So there might be subpopulations. And then I might want to know on average out of individuals like me, how does the treatment work? If we don't stratify like that, we might be able to just say something about the general population average. I consider that pretty lazy these days, but we're still interested in how do things behave on average. So I might not know how the individuals are distributed, but I might know if n is large, how this thing is distributed. So if n is big, and it's going to depend on the underlying distribution. How big does n need to be for this result to hold? Well, if this distribution isn't too funny, n doesn't need to be too big. Maybe n is 30. But if this is a very high-dimensional thing and it's very wiggly, then n would have to be a lot larger. So I'll give you a problem where you can experiment with some n's, and it might surprise you that sometimes it takes a while for the central limit theorem to kick in. But if n is big, then I can figure out what the distribution of this new random variable is. So I'll just call this x bar n, whatever this distribution is. It turns out this distribution, or this statistic, is about normally distributed. So approximately. And we might want to know which normal are we playing around with. So if we ended up knowing what the mean was and what the variance of the xi's were. And I'm going to give it a name, sigma squared. And I want to just point out, this thing has to be finite. So if I say something like variance of x is sigma squared and sigma squared is less than infinity, what I'm saying is that it exists. That the variance of these individuals exists. So I'll just say variance exists. So it turns out when this condition holds that there is a variance of the underlying distribution, then the distribution of my sample average is about normally distributed. So this is going to be normal with mean mu and variance sigma squared over n. And most of you know that. So the question is why does this happen? But this is really cool, that regardless of what this distribution is, the distribution of this is always about the same, so long as the variance exists in the first place. So if the variance of the underlying sample doesn't exist, i.e. it's infinity, this result does not hold. So, and that's your one condition. So we just need finite variance, and then this statistic is distributed something like this. So if I went back out into the population over and over again, and I resampled all these x bars, they would be normally distributed. And we saw that in our simulation. So even in that, when the underlying distribution of the individuals was trimodal, the average was unimodal. And I could even characterize what the parametric form of these tails are. With the bootstrap, we didn't need to know all that. We just construct it. So, more specifically, the central limit theorem really says this. So, x bar n is distributed normal with mean mu and variance sigma squared over n, meaning that as n gets bigger and bigger and bigger, the variance is going down. So I learn more, and I get closer to estimating what true mu is the repercussion of this. So what I mean by this is this. So I really mean that x bar n minus mu over sigma over root n, this is converging to a normal 0, 1. I think of the central limit theorem like this. That's probably what I'm going to do with it, and I'm going to estimate the distribution of x bar using this form. So the reason I can't just write this down and talk about this thing as n goes to infinity, that this becomes more and more true, because as n goes to infinity right here, that variance is going to 0. So I would be saying that as a function of n, I get this degenerate distribution with 0 variance. So I don't want to say that. So I'm going to put all the n's over on the left-hand side of the equation and standardize everything. And I'm going to say this thing is going to a normal 0, 1. And so this is going to 0, but x bar n is getting closer and closer to mu. So both of those things are going to 0. So I have everything in the limit on the left-hand side. There's no n's over here. So practically speaking, what we do with this result is when n is kind of big, then we might say x bar is distributed like that. So there's a little bit of a difference between the theory and the application of this, because in the application, you never see an infinite number of data points. So I use the central limit theorem like this, but in a technical sense, we're going to prove this statement. Okay, let's get to it. So this takes a couple minutes to prove this, but this is called the central limit theorem. So regardless of what this distribution looks like, this result's going to be true so long as that is true. Of course, if the original sample doesn't have a variance, taking an average isn't going to give you a variance. We'll look at a couple examples like that. Okay, we need a couple preliminaries. Taylor's theorem and moment generating function. So I'm going to try to do this relatively quickly. If you would like a mini class on Taylor's theorem, I could put one together during office hours. I'm going to hope that we all remember our calculus to some degree. And after we do that, I'm going to tell you all about moment generating functions. So let's just look at Taylor's theorem first. So I'm going to say, instead of the theorem, I'm just going to talk about Taylor's approximation. So it says if I have some function, f of x, I can approximate it using a polynomial. So I'm going to write down inequality, and then I'm going to write down an approximation. So I'm going to say k goes from 0 to infinity. So this is a little bit of theory, because I can't actually do this infinite number of times. So this is going to be the kth derivative So I think this is a statement that kind of reflects something that Taylor was saying. What people usually do with this is they'll approximate. So this is going to be finite. And then I'm just going to plug in these same terms. This letter C right here is my centering approximation. We'll call it the centering parameter. So this function right here is going to be about like this. And I'm going to be really good at approximating things around the number C. So around C, I approximate well. As I start to move away from that number C, I approximate less well. So I'm just going to write down, this is going to be f of x is going to be equal to this thing that we've been writing down. So this approximation plus some remainder. And we know what the remainder looks like. Remainder is just going to be k goes from cap k plus 1 all the way out to infinity, and then I have similar terms. Compute them exactly the same. So the remainder is just all the other terms. Taylor's theorem is all about this remainder. What do we do with Taylor's theorem? Usually we end up approximating something using this chunk. But the theoretical part that Taylor came up with is he said something about this approximation, and he said something specific about the remainder. So you know what Taylor's theorem is. What does Taylor say about the remainder? Bunker.
Isn't it that as you use more k's, that remainder will vanish?
Yeah, that's kind of true. Let me just tell you. So this remainder, all we have to look at is the biggest term in the remainder. And that biggest term governs the error that we make by using this approximation. So I'll just say, this is going to be f. So I'll just write down the remainder is governed by the biggest term. All these terms get they start getting smaller and smaller and smaller. So the biggest term is going to be this one, f cap k plus 1. So this is just the first term in the remainder. So this is the first term. Said you don't need to study this whole infinite sequence of everything to understand how good your remainder, how good your approximation is. All you have to do is compare this right here to the smallest term in your approximation. You're going to compare those two things to each other. So instead of having to look at this whole infinite sequence, we can just look at the biggest term in the remainder. That's pretty cool. So I don't have to study an infinite sum, I just have to study two terms in the equation. The term relating to cap k and the term relating to cap k plus 1. Bunker.
Shouldn't it be over k plus 1 factorial?
Say what?
Shouldn't that first term be over k plus 1 factorial?
Oh yeah. Yeah, for sure. Absolutely. So if you go back to your calculus book, they're going to teach you about something like the radius of convergence and where do you compute that. So how far from C can I move away before the approximation just falls apart? What you're going to do to analyze that is you're going to study the first term in your remainder. So this isn't a calculus class. I'm not prepared to go through all of those details, but hopefully this reminds you of what you learned maybe 4 or 5 years ago. Okay, so that's Taylor's theorem. You can kind of just work this out and figure out these terms just by going through and taking derivatives of this and evaluating it at C. And you'll end up seeing that a whole bunch of things go to 0 in your equation. You can figure out the coefficients, and the coefficients of your polynomial is this. So I won't do that derivation, but if you want to see me in office hours or after class to go through this, I'm happy to do that. Okay, so check.
What is the smallest term in the approximation?
Say what?
You said to take the biggest from the remainder and the smallest from the approximation. What is the chunk? here it's the small.
So I'm going to compare this thing, star, to f cap k, evaluated c, cap k factorial, x minus c cap k. So I'm going to compare the biggest term in my remainder to the smallest term in my approximation. And so you don't want this thing to explode compared to that. So this had better be small compared to that and not blow up. And so if it does blow up, more of your, there's more stuff going on in the remainder than there is in your approximation. And you want it to go the other way around. And so if you had that where this term was blowing up relative to this, you'd probably pick a different C or something like that. And so you would say, well, I could maybe get this approximation close, but only in some window of C. In calc class, they call that the radius of convergence. How far away from C could you move before the remainder started taking over and dominating everything in the approximation? Okay. And we'll use that result. So we're going to need that result, so I'll go through it in a little bit more detail. Because we're going to need it. And I think this whole lecture really is about explaining why the remainder is diving down towards 0, and it doesn't matter. So that's the most important part of this proof that we'll see. Okay, moment generating functions. We'll need two properties. So moment generating function is just the expected value of ext, where x has some density. So what I mean by this is some integral. Integrate e to the xt against its density. And I'm going to integrate over the entire space of x. Some people will call this the Laplace transform. So in probability class, we call this the moment generating function. If you're in an engineering class, they still do this. So if you're in a differential equation class and you see this, they just have a different name for it. So it's called the Laplace transform. And there's some utility here. So in the context of probability, I can take derivatives of this with respect to t and figure out what the moments are of the distribution. So what we do is we look at things like this. E to the xt. If I take a derivative with respect to t, this thing is going to be, I can slide that derivative sign through everything if everything is bounded well. And I wind up with e to the xt. And then I have to chain rule. And I take the derivative of e to the xt, it's e to the xt, and then I take the derivative of the subfunction. Derivative of xt with respect to t is just x. Then we go through and we evaluate this at t is equal to 0. I think that's pretty standard notation. But now we're going to plug t is equal to 0 into this. That's going to be the expectation of e to the 0 t minus x. This thing is just 1. So that's the expected value of x. We could do it again. We could take a second derivative. And then evaluate everything at 0. And this thing would be the second moment. And we could do it again, and again, and again. And in general, we could write n right there. And this will provide you the nth moment of the distribution. Now, these moments don't always exist. So if you did have a full set of moments and they all did exist, that would be equivalent. If I enumerated all of those, I would have just as much information about the whole probability distribution, and it would be characterized just by its moments. So for a normal distribution, we can look at just two things, the expectation and the variance. And the variance is comprised of two moments. All the other moments are 0. They do exist, but I only need to get the first two moments to characterize that distribution. So if you tell me something's normal, all I'm going to ask you for is the mean and the variance, which can be computed from the first two moments. So not all distributions have moment-generating functions, but when they do exist, they can be a nice mathematical tool for characterizing that distribution. So I'm going to presuppose that my original sample coming from that distribution does have a moment-generating function. Now, of course, distributions like t-distributions don't have moment-generating functions. So Cauchys aren't going to have moment-generating functions. Even worse, Cauchys don't have finite variance. So the CLT doesn't even apply to that. Okay, so moment-generating functions basically exist, when the tails aren't too heavy and the function isn't too wiggly and spiky. So usually what we'll say is under regularity conditions. So something like that, this sweeping statement that says the function's not too wiggly, the variance exists. Okay, there's a couple properties that we need. So I think I'll remind you of these two properties, then we're going to put everything together and finish this proof of the CLT. So property 1. So if xi's are coming from this distribution, and the moment generating function exists. So the MGF, and I'm going to give this some notation. So I'm going to say M, this is going to be for x, t, and this thing is just this expectation. So I'm just going to give it a little bit of notation. So if I wanted to know not the moment generating function of x, and I'm going to say this is IID right here. I maybe want to know what is the moment generating function for the sum of I random variables. And it turns out, in the IID case, this is e to the xt raised to the nth power. Let me just ask you a question. Who does not know this already? And it's okay if you don't. Okay, a couple. So I think next time I'll come in, I'll write down the proof of that. You might want to review it. It's just 1 or 2 lines. But there's also another property that I want you to review. Property 2 is going to be the MGF of some constant times our random variable. It's just going to be this creature. It's going to be the original MGF of x, but instead of plugging in t, I'm going to take t and I'm going to multiply it by c. So the moment generating function of the sum of IID random variables is the nth power of the original moment generating function, and the moment generating function of a scale of our original random variable is the original moment generating function, but I'm just going to scale C. And so if you understand this equation right here, all of that is almost immediate. So next time I'll come in, I'll prove those two things, and then we're going to get it underway and finish the central limit theorem. I think it'll take about 25 minutes. That's my guess, so that probably means it's going to take the full 50. So we'll see how it goes. Anyway, review these two properties, and it'll make everything much, much better. You can also read through the proof in the book. It's provided for you, but I think it's worth talking about for a couple of minutes. All right, thank you guys. That's it for now, and I'll see you next time. The nice thing about all these preliminaries is once we get them out of the way, we get to use them over and over again. So when we get to delta method, we'll need both of these tools as well.